Let's talk about the mass and center of mass of a lamina. The mass of a lamina, it's a thin metal plate that covers the region R, is m equals, well, this is going to be the double integral of delta of xy dy dx, where delta of xy is the density at the point xy. For example, a lamina covers the region in the xy plane bounded by the lines 2y plus 3x equals 6, x equals 0, y equals 0. The density of the region at the point xy is x squared y. Find the mass of the region. Here's what the region looks like. Now again, notice that the density, delta, equals x squared y. So for example, the density here at 0, 0, well, the density would be 0. But as x and y increase, the density increases. So in other words, it gets, you can think of it as getting heavier or denser as you move away from the origin. Okay, so again, the mass, m, is the double integral of delta of xy dy dx. Delta is x squared y. Here's the region we're integrating over. So the integral of x squared y dy dx can be rewritten, written in this way. X in this case goes from 0 to 2, and then y goes from 0 to 3 minus 3x over 2. That's because this line, 2y plus 3x equals 6, can be rewritten as 2y equals 6 minus 3x, which is y equals 3 minus 3x over 2. Okay, so x goes from 0 to 2, y goes from 0 to 3 minus 3x over 2. Those are the limits of integration. Here's our integral. Integrate with respect to x, and we get x squared y squared over 2. This is as y goes from 0 to 3 minus 3x over 2. So in other words, we have x squared times 3 minus 3x over 2 squared all over 2. We can integrate that easily enough. We multiply it out. This is the integral from the previous page. So what we'll do next is move the 2 to the outside and just make that a half. And we'll also multiply this out, 3 minus 3x over 2. We end up with 9 minus 9x plus 9x squared over 4, well, times the x squared. Multiply that out, this is what we get. Integrate with, so now when we integrate this with respect to x and plug in 2 and 0, this is what we get. Integrate with respect to x, we get 3x cubed minus 9x to the 4th plus 9x to the 5th over 20. Plug in 2 and 0, this is what we get. Plug in 2, we get this. Plug in 0, we get nothing. So we end up with 1/2 24 minus 36 plus 72 fifths, which is 1/2 times negative 12 plus 72 fifths, which is negative 6 plus 36 fifths, in other words, 6 fifths. So that would be the mass of the lamina, 6 fifths. Some calculus books foolishly use rho for density, but this is too easily confused with the rho from spherical coordinates, so we won't use it. I don't know what's going through their minds. It's just crazy. Okay, let's talk about the center of mass of a lamina. What is the center of mass? If you put your finger under the center of mass of the lamina, you'd be able to balance the lamina on your finger. So it's like a balancing point. If the density at the point xy is delta of xy, the center of mass of a lamina, a thin metal plate, that covers the region R, is x bar y bar. Here are the formulas for the coordinates x bar y bar. X bar is 1 over m, m's the mass, x delta, and y bar is 1 over m times the integral y delta. So again, for x bar, it's x delta, and for y bar, it's y delta. So for example, find the center of mass of the lamina in the previous problem. The center of mass of this lamina is x bar y bar, where x bar equals 1 over m times that double integral. M in this case, the mass, was 6 fifths, and x squared y was the density, delta. So we've got 1 over 6 fifths is 5/6, and again, the limits of integration are going to be the same as what we had earlier. And when we multiply this out, we get x cubed y dy dx. Okay, so it turns out that if you evaluate this integral, this entire integral, coincidentally, also equals 6 fifths, just like the mass did. So 5/6 times 6 fifths, that's 1. So that's x bar. That is our x-coordinate of the center of mass. Y bar is 1 over m times y, the double integral of y delta. In other words, it's 1 over 6 fifths, which is 5/6, times the double integral of y, x squared y. So we end up with this. Same limits of integration, and we've got x squared y squared dy dx. Okay, integrate this with respect to y. Integrate this with respect to y. and we end up with x squared y cubed over 3, and we let y go from 0 to 3 minus 3x over 2. So again, I left it off over here. I should have included it. We have a 5, 6 on the outside. So we have 5, 6 times the integral from 0 to 2 pi. Oh my gosh, there's no pi over there. What on earth am I thinking? Times the integral, integral 0 to 2, x squared, 3 minus 3x over 2 cubed, all over 3. Holy cow, do you want to multiply 3 minus 3x over 2 cubed? Do you want to multiply that out? I don't want to. So we're just going to use Mathematica. On Mathematica, or Wolfram Alpha, if we integrate this function, we get 6/5. And so our answer, it's amazing how this 6/5 keeps cropping up. So our answer is going to be 5/6 times this integral, which also turns out to be 6/5. In other words, 1. So that means the center of mass of this region, x bar, y bar, is 1, 1. And there it is. If you could balance this on your finger, it would balance right there at 1, 1. Now you may be thinking, no way. There's no way it's going to balance there because it's clearly off to the side. It would tip over. But recall that the density of the region of the point xy is x squared y. So it actually gets denser as you move further away from the origin. So I think it's entirely reasonable that if you put your finger there, it would balance. Okay, one last application, the electric charge of a lamina. It's electric. If the electric charge at the point xy is f of xy, the electric charge Q of a lamina, thin metal plate that covers the region R, is simply going to be Q times the double integral of f of xy dy dx.